Greetings everyone. Let's go to 8.3 where we're going to solve differential equations using Laplace transform. So far Laplace transform seemed to be a little bit disconnected from what we were doing before, but here it's where everything fits together again. And so what we need to know first is, okay, if you have a function f and we can calculate the Laplace transform of this function. So functions that have the Laplace transform, there are some conditions that you have to satisfy. One of which I'm going to mention in the next result here. I didn't make it very explicit before, but I'm going to tell you this is part of the conditions on which we have Laplace transforms. But okay, so if we have a Laplace transform, which we then, so this is the variable t, we normally write this with the variable s. We could ask, okay, do we know what the Laplace transform of this guy is? Of the derivative of f? That would be nice, at least that we know how Laplace transforms behave with derivatives. And yes, the formula is very simple, but okay, you have to pay a little bit attention to it. So I'm going to write it in terms of y, because that's how we're going to use it always. Ly prime, but y stands for function f, right? Is s Ly minus y0. So this is the Laplace transform of a function. The derivative of a function is you take the Laplace transform of the function, multiply it with s, and subtract the initial value if you want, at 0. And we will always have, in this section, the initial conditions will always be at 0. Okay. So that's a nice formula, and we can try to verify it, for instance, on the sine, because we know that the derivative of sine is cosine. But that's done in the book. Rather than do that, another thing that's in the book, I wanted to show you, like, where does this come from? Okay, where does this formula come from? Because I don't want you to just learn formulas out of the blue, okay? There is a reason why this formula is true, and while my argument is not fully 100% solid, it is fine enough to convince you that that this is true. Okay, so I'm going to have now again. I'm going to calculate this guy. So I'm going to write f again instead of y, because it's easier to write with a function to use it to name it f than y. I don't know why, but that's how it is. So, okay, so by definition, what is this? By definition, this is this, right? E minus st f prime t dt. That's what the Laplace transform of function is. So, and so here you put in the function, and our function is f prime. So that's why the f prime goes in there. Okay, so let's look at this indefinite integral first. Okay, and I'm going to use an integration method that we know before, namely integration by parts. I'm going to do integration by parts. Now, technically, this is not what you've been told. This is not ILATE type, right? But this is a theoretical argument. So here, it's allowed. We can do this whenever it works, right? And so what we're going to do is, well, okay. Remember, in integration by parts, you're choosing a u and a dv. So, and you have to divide. You have to divvy up all these things between u and dv, but of course the dt goes always with dv, and then whatever you call a dv, you better be able to integrate it. Ah, professor, I know how to integrate f prime, because that's just f. The integral of f prime is f, right? Integrals are antiderivatives, so they cancel the derivatives. Okay, so all right, so let's take that then as our dv, and what's left is e minus st. Okay, so once we have done this, we have to calculate du. Now remember, the variable is t here, not s. Okay, this is clear from this expression here, also from here, right? Okay, so du is then minus s e minus st dt, and v is equal to, well, as we said, f of t, because that's the antiderivative of derivative, is just a function. Okay, so this is now equal to u v minus integral v du. So this is equal to, let's plug everything in, u e minus st v ft, okay, minus v ft du minus s e minus st dt. Okay, good. So let's go back to our Laplace transform. This is now an improper integral, but we are being a bit sloppy with improper integrals, and we just pretend that infinity is an endpoint, right? It's really a limit that we have to take, so let's do that. So we put here 0 and infinity, right? This function is a function, there's no integral anymore. Here we have an integral, so we put the endpoints here. Now let's bring this minus s, because can I do that? Yes, because s does not depend on t, right? In this whole story, s is something new that is independent from t. Okay, it eventually becomes a variable, but each time we integrate, we think of it as a constant. So we get a plus s here if I bring this out, okay? And then what is left is this guy. Well, let's look at this one first. This is something you should recognize. If I just flip around the e and the f, oh, this is just the Laplace transform of f, right? We're trying to link the Laplace transform of the derivative with the Laplace transform of f itself. So only remains this thing. So there's two things here. What happens if I plug in infinity? So we get e to the minus infinity f infinity minus, and now plug in 0, 1 times f of 0. You get me? And so this was, we said LF, so let me write it here. The Laplace transform of f, right? This was that. So the only thing is, what is this here? And this is where I need to invoke something that I just briefly went over. In order for the Laplace transform to exist, this has to be 0. So, so if you want a function that has a Laplace transform, well, I shouldn't say that's the only thing, but we will only look at functions that satisfies this growth condition, because this is a growth condition if you think about it. What this says is that, okay, so remember, in general, f will tend to infinity, and this tend to 0, so get 0 times infinity, which is an indeterminate form. But very often, when, for instance, f is a polynomial, we know that this grows much, much slower than this decays. So the quotient, if you can also write it as this way, right? You can write it as f infinity over e infinity. Okay, that this guy is so growing much less quickly to infinity than this one, that the result is 1 over infinity, which is 0. Okay, we call this exponential growth, at most exponential growth. We say f is a most exponential growth if this quantity is 0. It's not a quantity, right? Technically what it is, it's the limit for t going to infinity, for, well, I don't know, z going to infinity of f z over e to the z. So this is, if this is 0, then the Laplace transforms exist, and I mean, assuming our f's always satisfy this. Okay, so that means now let's write it in the opposite order, right? So this is 0, this is a minus f0 LF, and this is exactly the formula that I wrote down here. Okay, you see where the s comes from? The s has come out here, right? This is where the s is. I forgot to copy the s. The s was there and I forgot to copy it. So now it matches. Okay, so that's great. So now we could ask, okay, what is then the Laplace transform of the double derivative? Okay, all right. So, well, we know we can think of the double derivative as the derivative of y prime. And then the formula, this is the formula. So I'm using this formula, but instead of y, I plug in y prime. If I plug in y prime for y, this becomes y double prime, this becomes y prime, and this becomes y prime. Ta-da! But this one, again, now I do the actual formula. This is s times ly minus f minus y0. We're going to use y's this time. Minus y0. So if I now, and then we have, of course, this guy, so let's recopy that. And now if we expand, we see s squared ly minus y0 s minus y prime 0. That's ly double prime. Now, you might want to memorize this formula or use this formula. That is fine. Because what we're now going to do, so why were we doing this? Well, here is an example. I'm going to go straight to an example. Let's do this one here. Okay, let's look at the following differential equation. Y double prime minus 6y prime plus 5y equals 3e to the 2t, and we have initial conditions. Y0 is 2, y prime 0 is 3. Okay, so let's analyze what this is. We can solve this. We have methods to solve this one before. So perhaps in a quiz I ask you to do it 2 different ways. Okay, so this one is a constant coefficient second order linear differential equation. So we know if you solve this first, you take, and this is a function that is of a particular type, an exponential times a polynomial. Okay, so to solve this, there were 2 steps. We solved homogeneous, which correspond to characteristic equation, blah 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 blah, and then we do the forcing. We have this forcing function. There's, remember, there was y equals u and so on. Okay, so review this if you don't remember how to do this anymore. I'm not going to do this in the lecture today, but I might do it in a homework video or something like that. Okay, so here, what we're going to do now is totally different. We say, okay, notice that I'm using t as a variable because with Laplace transforms we prefer t to be the variable instead of x. I'm going to use Laplace transforms. Da-da-da. Okay, here we, because, I mean, come on, it's differential equations, and you introduce this weird thing, and you're not going to use it? Yes, we're going to. So let's do the Laplace transform of both sides. Okay, let's do it the right hand side first, because that's a function, we know what that is. We know that this is, well, 3 comes out, that's just a constant. The Laplace transform of an exponential, that is 1 over s minus the shift, which is the factor in front of here. So the a is 2 here. So a is 2 in this thing. Okay, so that is where we get this guy from. Okay, now what here? Well, Laplace transform, we have said, it goes through a linear combination. So we can write it as Ly double prime minus 6 times Ly prime plus 5 times Ly. Okay, so now for this is equal to 3 over s minus 2. So I'm going to now introduce a new variable that I'm going to call capital Y, that is the Laplace transform of little y. Remember, we have f, and the Laplace transform is f, often denoted by the same letter but in capital version. So I'm doing the same thing here. So y corresponds to capital Y. But capital Y is something we don't know yet, okay? And so now we can use our 2 formulas here. I'm going to repeat them to write them here, so I'll box them here. These are the 2 formulas that we will need. Is the Laplace transform of y prime is the, so remember, Laplace transform of y is now capital Y, that is s capital Y minus y0. Let's look at this formula, except that I now wrote this as capital Y, okay? And what is then the Laplace transform of the double derivative? We have the formula right here. Okay, so this becomes capital Y, and the rest is whatever it is. So this is s squared capital Y minus y prime 0 s minus y0. So, sorry. I wanted to say, be careful to write the right places where y0 and y prime go, right? So, yeah, so this is how it goes, right? In the first derivative, the Laplace for the first derivative, we only have the y0. In the second one, we have both of them, and the y0 becomes the coefficient of the degree 1, and this becomes the coefficient of degree 0. Okay. Okay, so now let's plug everything in. So s squared, I'm going to put this one here. So s squared y minus y, oh, wait, I know what y0 is. Remember, y0 was, they gave us to us, so let's not be dense about this and write them up. So this would be sy minus 2, and this would be s squared y minus 2s minus 3. Okay, so s squared y minus 2s minus 3, that is y double prime, minus 6 times, now the L of the y double prime, L of y prime, that is sy minus 2, plus 5, and L, what is this? Well, that's just y. And that is equal to 3s minus 2. Okay. So what we get is actually no longer a differential equation. This is just a function. Think of y as the undeterminate here, and we just gonna solve for y. So that's really what we do. We're gonna solve for y. Okay, let's work it out. That is s squared y minus 2s minus 3 minus 6sy plus 12 plus 5y equals 3 over s minus 2. So the terms with the y's in s squared y minus 6sy. Okay, let's put the y already out here, right? I'm going to put the y out of the terms. So we get s squared minus 6s plus 5 y, s squared minus 6s plus 5y, and equals, I'm going to bring these all these guys to the other side, 3 over s minus 2 plus 2s plus 3 minus 12, so that it will be minus 9 here at the end. Sorry, minus 9. Okay, and so we're solving for y. First of all, I'm going to put this on common denominator, 3 plus 2s minus 9 times s minus 2 over s minus 2. Now, normally we expand this, but for what we're going to do, it's not necessary. And so let's avoid extra work, and in fact it will make life a little bit easier that we don't. Okay, so I'm not going to expand this. So this is one of the few cases where we don't do this. Okay, there's no harm if you do, but here we don't do this. So this is what we get, and now we divide both sides with this factor here, right? And so we get y equals 3 plus 2s minus 9 times s minus 2 divided by s minus 2 times s squared minus 6s plus 5. Now, notice that it is no coincidence that this s squared minus 6s plus 5 is actually the characteristic equation of our of the corresponding homogeneous equation, right? If you remember how the characteristic equation goes, that's exactly what it is. Instead of t, we have now a variable s. Okay, so that's no coincidence, but I would just suggest work this out. I want you to work this out, not just the formula. The book gives the formula, says, oh, you can plug it in right away. Why? Just do it. Just look. There's not looking up the formula is going to take more time than writing it up. Okay. Now, what we do need is okay. So where are we at now? This y, remember, was the Laplace transform of y. So don't forget. So let me keep that in mind. So this is where I perhaps should box it, right? This is a formula that I have to return to. So what I need to do is to find y, I'm going to have to take the inverse Laplace transform of this whole huge big thing. Now, we have exactly done this in the previous section. And that means we're going to need to write this as a partial fraction, and then we should be able to do this. Okay, so so to make this a partial fraction, we have to factor it completely. Now, is this a quadratic reducible, the second term in the denominator? No, it is a factor in the denominator. No, it isn't. We can factor this. S squared minus 6s plus 5 is s minus 5 times s minus 1. Okay, so we find y is equal to 3 plus 2s minus 9, s minus 2 divided by s minus 2, s minus 5, s minus 1. Doesn't matter in which order I write this. So we need to write this as a times s minus 2 plus b times s minus 5 plus c times s minus 1. We know that it's possible, the a, b, and c's. And since there are distinct roots, so they're all distinct, luckily we can use the term Heaviside to calculate these numbers very quickly. So a, what we do, we take this whole big expression, and then what we do? Well, we look at a is on top of the factor s minus 2, so we scratch that factor out and we plug in s equals 2. Okay. Oh, this is nice because you notice that this already is now 0. That's why factoring was good, because this will always happen, at least for one of them. So this whole thing is 0, so the calculation is even very quick here. On top is just 3, and in the bottom I'm plugging in 2, so it's minus 3 times minus 1. So all this is equal to 1. Okay, A is 1. So as always, I'm going to cheat a little bit by erasing it and do my calculation over for the next one. A, now I'm going to do B, right? So for B, now the factor B is on top of S minus 5, so always check what is the factor, S minus 5, because I didn't write it in the normal order, so always check. S equals 5. I have to plug in now. Okay, now in the top you have to plug in, but see, expanding is not going to help you. In fact, you see the calculation comes a little bit simpler here, because 2 times 5 minus 9, that is 1, times 3, and in the bottom I get 3 times 4. So I get 6 divided by 12, so I get a half. Okay, so B is a half. And then finally C. So we don't do this, we get a different number here. C is now the factor that we're dealing with is S minus 1, so this gun goes and we plug in S equals 1. Okay, so in top we get 3 plus, the dot is just a straight dot. 2 minus 9, that is minus 7, 1 minus 2, that's negative 1, and in the bottom I get minus 1 times minus 4, so I get 10 on top, minus 4 on the bottom, if you want minus 5 halves. Okay, so I can make this into minus 5 halves. So this is the inverse, remember, y is the inverse Laplace transform of, y is the Laplace transform of y, so we know that little y is the inverse Laplace transform of capital Y, and we can now, from this form, write down right away. We have the first one they're all single powers, right? So we know that it is going to be it's just an exponential given by the shifts here. The first one is 2 plus a half, that's this coefficient, right? And the A is here 5, and minus 5 halves ET. So you see it kind of rolls out why are my signs different? Sorry, did I? Did I calculate my signs? No, let me see here. Yeah, I lost a little bit my calculation, so I might have copied the wrong signs. They have a negative sign for this and a positive sign for the third one. I'm attributing this to a mistake because, I mean, okay, this one, the calculation is still up here, right? So, and I have the same formula, let me double check. I think there's a copy error in the book. I'm going to leave it this way. For one thing, well, I cannot tell. Yeah, right, okay. So that's the solution. So you see, it's a different method. Some things are kind of similar, right? Because we still have to factor the characteristic polynomial and so on, but okay, it's a different way. Now, one of the disadvantages is that we only have a particular solution, namely the one given by the initial conditions. Okay, you can use it also for the general solution, but it gets a little bit more, well, complicated. Let's do another one here. 2y double prime plus 3. Let me see. Is this the one I want to do, or is the next one? Okay, let me do the next one. Sorry. So y double prime plus 2y prime plus 2y equals 1. Initial conditions, negative 3 and 1. Okay? And so now we're gonna do again the same thing. We apply the Laplace transform and we write capital Y for the Laplace transform of Y. Okay, so we get y double prime plus 2 times ly prime plus 2 ly. So as I said, I would like you to do this. Okay, now what is the Laplace transform of 1? That is 1 over s. Okay, that is just straightforward. Now this one, from the formula, this is s squared y minus s times y0, which is negative 3, so plus 3s minus 1. So remember, this is here, the formula, right? We take the, the double product, right, the double one. So here we have minus y0 minus y prime 0, minus y0 s minus y prime 0. So minus y0 minus is 3s minus y prime 0, 1. That's the one, okay? Plus 2, here we have sy minus the initial condition at 0, that's plus 3, plus 2 times y, and that's equal to 1 over s. Okay, so we get s squared y plus 2s y plus 2y. We know that we're going to get this. I can factor out the y here, right? So let's factor out the y. And we do get the characteristic polynomial here. That's always, for me, it's more of a check. Okay, I'm right, okay, rather than putting in the formula. What else we have? We have a true 3s minus 1 plus 6, that's it. And that is equal to 1 over s. So this is s squared plus 2s plus 2y equals 1 over s minus 3s, and this was plus 5, so it becomes minus 5 here. And put this on common denominator, is 1 over s minus 3s plus 5 times s. And again, we don't expand. Okay, so finally, capital Y is equal to 1 minus s times 3s plus 5 over s times s squared plus 2s plus 2. Okay, and now we have to just calculate the inverse Laplace transform. So this is the material from 8.2. So we have to factor the denominator further if possible, but this is not. So this time this is a quadratic irreducible. Now for quadratic irreducible, we know what we need to do. Okay, so we now know we have to first find the center of it. By completing the square. Okay, so complete the square. Sorry, that's what I'm doing here. So this is done. We separate a little bit the constant term. We plug in what we do. We divide by 2. Divide by 2, then we get 1 here, and then we square it. And that gives me a 1. Now, of course, if I put a 1 there, I have to subtract the 1 to make it equal. So we see that this is equal to s plus 1 squared plus 1. So we know that this partial fraction here, y equals whatever this top 1 minus s 3s plus 5 over s squared plus 2s plus 2, I'm going to write it one more time, can be written as as, that's the single factor, that is okay, plus, and then we're going to write this as a polynomial in s plus 1. Okay, that's the whole s plus 1 squared plus 1. Okay. We clear denominators, we find that 1 minus s times 3s plus 1. Still, you see, I'm not expanding because at no point I need expansion. I just plug in numbers. So whether I plug in a number in a factored form is sometimes a bit easier. It's less plugging in. Equals, now be careful, of course, I skipped this step. I'm not going to do this. This one you have to do on your own to make sure that that's what you get after you clear denominators. And don't forget to put everything between parentheses here. This thing between parentheses, that's the one that we forget. Normally they don't forget this one, although here we don't need it. But this is the one that one forgets and then gets confused about it. So, okay, that is what it is. And so now we plug in values for s. So first we look at roots. So s is 1. S is 0, sorry, s is 0. The root, we are referring to the root of this of this denominator, but there's only one, that is this one. So s is 0, we see that over there we get 1 on the left hand side, and the right hand side, this whole thing cancels, we get a times 2. So we see that a is a half. Okay. Next one is the center of the quadratic irreducible, if possible. This would be -1. That's the thing that makes this guy 0, right? So if I plug in -1 on the left hand side, I get 1 minus minus plus minus 3 plus 5, and that is equal to a, because this is 0, plus minus c, the -1 there. Okay, and okay, so this is 2, this is 3 on the left, and this is a half minus c, so we see that c is equal to a half minus 6 halves, so that is minus 5 halves. And then finally, to find another value. There's nothing special we can do anymore. We like to plug in 0, but it's already been used, so the thing I'm going to use is s is 1. Okay, if I plug s is 1 on the left hand side, I get 1 minus 8 equals 2 square, that is 5a, plus 2b plus c times 1, but okay. So that's minus 7, a was a half, so this is 5 halves, plus 2b plus c, that is minus 5 halves, the 5 halves cancel, and so we see that this b is minus 7 halves. Let me see, is this the thing? A half minus, yeah, I think I seem to get the same numbers. So let's write down what we have. So we find that y is written as a half over s plus minus 7 halves s plus 1 minus 5 halves over s plus 1 squared plus 1. Now, to find the inverse Laplace form of this one, we know we're going to even split it further. So that is this minus 7 halves. And then the fraction is s plus 1 over s plus 1 squared plus 1 minus 5 halves. And this is 1 over s plus 1 squared plus 1. Okay, so this one is very easy. This is a non-shifted constant, right? The inverse Laplace of 1 over s is just 1, so this is just a half. Now here we have the variable on top, and in the bottom we get the variable squared plus omega squared, so here we see that omega is 1. Of course, that's the same here, right? This always come in pairs. So omega is 1, so that means that we have minus 7 halves, and when the variable is on top, that's cosine. So this is a cosine, right? Cosine, but there's a shift. A is -1, don't forget, it's minus minus, so this, okay, so omega is 1, so this is t, and the shift is e minus t here. Oh, and I don't know why there's an equal sign here. We're adding all this up. Okay. And then we have a minus 5 halves. This is a sine. The omega is 1. And there is a shift, the same shift, e minus t. Okay, so that's our solution. Okay. And you see, in particular, this case, it goes rather quick. The only thing is you have to do a partial fractions, which is if you would solve this using the methods from before, from the chapter whatever 5 that was, the calculations are different, and so depends on what you, I'm not sure how many people like partial fractions, so therefore this might not be the favorite method for many, but still I want you to know this, okay? And so for the rest I'm gonna not do any examples. I'll still do some more examples on the homeworks, including perhaps some well, yeah, okay, that's what I'll do. Some other cases also. And there's one more thing. The next lecture, what is this going to be? Well, so it's going to be now using this method to solve linear second order differential equation with constant coefficients, this type of equation. So that's what we're going to try to solve. But what if this function is no longer of the forms? Now, remember, what forms have we learned in chapter 5 and chapter later that we could solve in the chapter 6 on harmonics? Is that if this is an exponential times a polynomial or an exponential times a cosine or sine. Well, we didn't do the exponential with cosine sine thing, but that can be done too. But if this is a more complicated function, then we cannot use that method anymore, the method of indeterminate coefficients. And that is exactly where these Laplace transforms come in handy. We will give a general method to solve equations where this forcing function is more complicated. And this is necessary, right? Even in, remember the second order differential equations, this harmonic movements like springs obey this, Newton's gravitational law, mixing laws, cooling laws, well, there's our first order, but gravitational mechanics is actually second order, right? Although we solve them as first order, but now we have a more general technique here. Also, we saw RLC circuits are given by this kind of things, and the forcing functions could be sometimes more complicated, not just exponentials or sines, but for instance, what if it's an ln or something like that, okay? And so then the question is, how do you solve this, okay? That is the last section that we will deal in, that's the next video.